Hi folks, Mr. Ackerman here. Thanks for watching. Topic of today's video is acceleration. And what I'd like you to do in a moment is just pause the video, have a look at the first screen here where we will talk about, or where you can have a look at what we're going to be tackling today. Take a look at the homework schedule where we're at, as well as the learning goals and success criteria. Okay, and you're back, so you've had a chance to look at what we're going to be covering. And before we dive into things, I just want to point out that something a little tricky is going to happen here. The term acceleration in physics means something a little bit different than what it means in your regular English vocabulary. You've experienced this before. Remember when we learned about speed versus velocity? Probably you used to use the word speed and velocity interchangeably as if they were the same thing, but later you learned that they're actually quite different. Speed uses distance and velocity uses displacement, and that can lead to some weird things. For example, we learned that if someone drives in a circular track and makes one complete circle, then her displacement is zero, which means her average velocity is zero, even though she was moving. So because of the physics definition of velocity versus speed, you had to be careful when you do your calculations. The same thing's going to happen here with acceleration in physics. It might mean something different than what you think it means, so pay attention to the symbols, pay attention to the definitions and the equations, and you should be fine. All right, here we go. First off, I'd like you to take a look at a couple of pictures that I have here. I got these images of Formula One racing cars off of a Formula One site, off of Google image search, and I'd like you to imagine going to one of these races. It would be very loud, very noisy, and very fast. And I'd like you to take a look at the first picture here, where what I've done is to place this F1 car at different places along a straight track. And what I want you to imagine is that each of these images is occurring at equal time intervals. So for example, if this was time t equals 0, then I'd like you to imagine that this is maybe time t equals, I don't know, it might be 0.1 of a second. You know, these cars are very fast, they can move very far in short periods of time. Imagine if the car is speeding up. So it moved this far in the first tenth of a second, but because it's speeding up, it's now going to move farther in the next tenth of a second, so maybe we'd have something like this. And for that matter, it's going to move even farther in the next tenth of a second, so this might be 0.3 of a second. This shows us what we definitely call acceleration in the English sense and in the physics sense. The velocity is changing. The object is speeding up. So what you thought acceleration meant is actually what it does mean so far. Now let's take a look at another one. Here I've got the reverse. The object is maybe slowing down. So the object here is already moving, but imagine that at time 0, well, it starts here, because it's already moving. Sorry, there's an announcement coming over the PA, so we just have to talk over that and wait till they stop talking. There we go. Sorry about that. At time 0, the car is right here. Because it's already moving and it's about to slow down, therefore it's going quite fast in the beginning, and in the first tenth of a second we might expect it to go quite a bit farther than it did in the previous example. Now, as a car slows down, it doesn't go as far in successive time intervals, so at 0.2 of a second we don't go quite as far as we did in the first tenth of a second. And the same trend continues in the last tenth of a second. So this would be an example of slowing down. Now, in English, you call that slowing down or deceleration. So that's kind of like an English term. But here's where some of the confusion begins. In physics, this is also an example of what we call acceleration. So acceleration isn't just speeding up. It also includes slowing down. In fact, if we talk about the definition of acceleration, what it really is acceleration equal to the rate at which an object's velocity, sorry, that doesn't look like the word velocity, let's fix that up, the rate at which an object's velocity changes. Now, a couple of important components here. First of all, we are going to be talking about velocity, so there will be a v somewhere in the formula. And we've got the word changes, so there will be a delta somewhere in the formula. We've also got this word called rate. Rate meaning as time goes by. So at what rate does the velocity change over time? So there will be a delta t in the formula as well. In fact, the formula for acceleration, the symbol is a, and we're going to start off by computing, just like with velocity, an average. So we have average acceleration here is actually defined as the change in velocity, delta v, divided by the change in time. Now, of course, you may remember from previous science courses that whenever you see the word delta, whenever we're calculating a change, you can write this. You can write final value, so the final velocity, minus the initial velocity. And I'll show you an example of that very shortly. This is where we end up with our formula, and this is actually the formula for average acceleration. And I'm going to talk more in a moment about how exactly I got that final minus initial business and what that's all about. But right now, here's your new formula for this particular section. It's v final as a vector minus v initial as a vector divided by delta t. Now, why does delta v get written as final minus initial? Well, let me give you an example that has nothing to do with velocity, but that you'll be able to relate to. Imagine you get up in the morning and the temperature outside is really warm. The day starts out really warm. Suppose the initial temperature is 10 degrees Celsius. That's not very warm compared to the summer, but at this time of year, I'm doing this in the fall, of course, 10 degrees is not bad. Let's call this temperature 1 because it's in the morning. Let's say throughout the day, the temperature falls so that temperature 2 in the afternoon is only 3 degrees Celsius. If I asked you for the delta in the temperature, in other words, the change in the temperature, if I asked you in English, you'd say, oh, the temperature went down by 7 degrees Celsius. That's easy to see. But if I asked you mathematically for the result, how would you get the mathematical equivalent of down by 7? You would do T final, T2, minus T1, T initial, and what would you get? You'd have 3 degrees Celsius minus 10 degrees Celsius, and that would be negative 7 degrees Celsius, which is exactly what the English term down by 7 degrees means. So this idea of final minus initial to find the change, it really does work, and that's what we're going to use in this section. Now I'm going to delete this part that I just did here because it's really not part of acceleration. It's just illustrating why we use the delta symbol. Okay, so getting back to acceleration, average acceleration, it's v final minus v initial. So we're going to be subtracting two velocities, and when you subtract two velocities, of course the units you're going to get will be meters per second, or they could be kilometers per hour. It depends on what units you are using. The time, let's assume if you're in meters per second, let's assume you'll also be using seconds for your time. But let's also assume if you're using kilometers per hour, you might be using seconds, but you might be using hours as well. It really depends on how much time is going by and what the velocities are. For a race car, you'll measure times over tiny fractions of a second, and therefore seconds is going to stay down here. If you're talking about the motion of maybe an airplane that's flying from place to place, maybe you'll use hours. You have to look at each situation separately. But what I do want to point out is, what would happen if you were using meters per second as your velocity and you had seconds in the denominator as your time? Then this fraction here would come out to meters per second in the numerator divided by seconds in the denominator. That would give you units of meters per second squared, which is a very strange unit of measurement. You've never seen seconds squared. It doesn't mean like the area of a second. That doesn't have any meaning. The way to think of this is meters per second, that's the numerator, per second, as if to say my velocity is changing by a certain number of meters per second every second. Alternatively, you might use kilometers per hour and you might use seconds also as your time. Then you'd have kilometers per hour per second, which is as if to say my velocity is changing by a certain number of kilometers per hour every second. And of course, you might use kilometers per hour as your speed, your velocity, and hours as your time. There you'd have kilometers per hour, which is as if to say, my velocity is changing by a certain number of kilometers per hour every hour. And of course, that would become kilometers per hour squared. So definitely strange units for acceleration that you'll have to get used to. All right, moving on. Sorry, folks, I just need to pause the video for 1 second, so bear with me here. I will be back. Okay, folks, sorry about that. I had to go for a second to take care of something, but I am back, and let me just figure out where I'm at here. There we go. We were talking about the units of acceleration, and now we're going to get into an example here. Oops, there we go. Okay, so I'd like you to imagine that you are you're at the Olympics and you're watching the 100-meter sprint, for example. And this is a question that's out of your textbook. The textbook is Physics 11 by Nelson, and sorry, not by Nelson, by Addison Wesley, I apologize. And this is a practice problem in section 1.4. They talk about a runner who takes a small fraction of a second to get off the blocks after the starting signal. And if you guessed that this is the reaction time of the sprinter, you are correct. He rapidly accelerates to top speed. The velocity and time data for the 6 seconds of the race are summarized in table 1.8, which is right down here. And then they ask you to calculate a few things about the acceleration. Now, what I did was I took these data and I plugged them into Microsoft Excel, and I created a graph, which I wanted you to see, just to help give you another visual about what's going on here. This is a kind of graph that we call a velocity time graph. We haven't studied these yet, that's the next section, but I think you can appreciate that if you plotted the time along the bottom and what the resulting velocity was, you would get some sort of curve that shows that in the beginning, here's the reaction time right down there, not going anywhere, and then a sudden speeding up, but then gradually, remember they said that the runner reaches top speed very quickly, can't speed up very rapidly anymore, and so he kind of levels off at a top speed. And they're trying to say that the top speed is something like 12 meters per second, which sounds pretty accurate for the world's best sprinter. And what are the times that it takes to get up to that speed? I don't know if 4 seconds or 5 seconds is exactly right, but let's imagine that it is, because what I'd like to do here is use this visual as well as the problem here to answer some of these questions. Question number 1, calculate the average acceleration between the 0.123 second mark, which is when the guy actually began running, and the 0.5 second mark. So let's apply our formula, which we learned in the previous slide. Right back here, we learned that average acceleration is final velocity minus initial velocity divided by the time taken. And we're going to apply that right here. So here are our times and corresponding velocities. This will be like the initial, so I'll write initial in there, and this will be like the final, which I'll write in there. So here's what we do. For part A, we write A average equals V2, a little bit clearer there, V2 minus V1, or you can use the words initial and final, it's up to you, divided by delta T. Now the V2 here, the final, is 2.4, and they're asking for a velocity, so you have to include direction. Remember, it's a vector. Meters per second, the direction is forward. I'm just going to use the letter F there for forward, minus the initial velocity, which is 0, divided by the time taken, 0.123 minus 0, the starting velocity. And if you calculate that, you'll end up with 2.4 meters per second east divided by 0.123 seconds. And if you run that through your calculator, you'll get some number. I'll just fire up my calculator here. I'm using the one on my phone, so pardon me while I get to the app. What do we got here? 2.4 divided by 0.123. I get a number like this. 19.5 with some other digits meters per second, which is telling me that every second that goes by, his velocity increases by 19.5 meters per second. Does that mean that he'll get up to 19.5 meters per second? That's a really high speed for a runner. I don't think any runner's ever gone that fast. No, it doesn't mean that, because he doesn't do this for more than a very short period of time. In fact, with this much time, this acceleration gets you up to 2.4 meters per second. Another thing we can do is condense this unit here. Instead of meters per second, which is a bit of a mouthful, we can write it as meters per second squared. And of course, acceleration is a vector because velocity is a vector, and velocity helped us calculate acceleration. So there is that as well. You can go on and continue this problem on your own. The idea is similar. Part B, find the acceleration between 3 and 4 seconds. So now, I'll show you this in a different color, between 3 and 4 seconds, here with this velocity, and here with this velocity, do the same thing and see what you get for the acceleration. I think you'll start to notice that the acceleration you get in part B using these numbers is going to be a lot lower than the 19.5 that we got here. And you might wonder, why does his acceleration tail off toward the end? And the answer, of course, is that you can only run so fast. Maybe he gets tired. You could also look at the velocity graph and see that his speed starts leveling off. The velocity starts leveling off, indicating no further acceleration. All right? Once we get to the final part of the run, I'll highlight this in red, you can see that his velocity doesn't change at all. So in here there's actually zero acceleration. And it is correct, if you were thinking, when he's moving with zero acceleration, it means the velocity is steady, it's constant. All right, so there's a little intro into acceleration. I'd like to also talk about a strange example where you might not think there's acceleration, but there is actually acceleration. I'd like you to imagine that you are driving or walking or running or doing something in a circle. So you're going around like this. Let's imagine it's your car. You're making a circle through in the car, and you look at the speedometer. And let's imagine that your speedometer shows a constant value. I don't know what value this might be. Let's pick a nice easy number, 50 kilometers, oops, not per meter, kilometers per hour. Suppose that's what the car speedometer is saying. And you drive in a circle and you keep this pinned right at 50 the whole time. So my question to you is, are you accelerating? Pause the video and think for a moment. If you drive in a circle, with a steady speed, no change in the speed, are you accelerating? Pause the video and think about it. Okay, and you're back. And if you guessed that you are not accelerating because your speed isn't changing, then you could be forgiven. Yes, you're actually wrong. You are accelerating. Why are you accelerating even if your speed is constant? Well, remember, acceleration is defined not as the change in speed divided by time, but the change in velocity. All those vector symbols that you run into, they mean something. And here they're telling you it's the velocity that matters. Let's take a look at what happens to your velocity as you go in a circle. When you move on a curved path, your velocity vector points on a tangent to the curve as you go. So if a car is driving along at these various points, all we do is draw a tangent, and that shows us where the car is moving at any moment, in what direction. Of course, the steering wheel's turned, so the velocity vectors keep changing. So now, if the definition of acceleration is change in velocity over change in time, now let me ask you, here's your velocity at one moment, here's your velocity at another moment, and here's your velocity at yet another moment. Is that vector changing? Yes, it is. While it may not be changing in magnitude, it is changing in direction. So yes, your velocity is changing because the direction is changing. And that is part of velocity, therefore it's part of acceleration. All right. Moving toward the end here, I do want to show you a fun little simulation, and this is from PhET, which we've been to before. These guys at the University of Colorado, great physics simulations. The simulation's name, which is under the physics section, is called Motion in 2D. So here's what I'll do. I've already loaded this up so that we can see it. You're going to go to PhET, and you're going to go under Physics, Motion, Motion in 2D, and somewhere on my computer here, I have this. I have to find it. I think that's it right there. Okay, so I've downloaded this. It's safe to download. And what you do is up here, it asks, what vector do you want to see, velocity or acceleration? I want to see both. And then it says, do you want the ball here to undergo linear, so straight line acceleration, option 1, linear acceleration, option 2, something called simple harmonic motion, which we haven't discussed yet in our course, so ignore that for now, circular motion, which we study in detail in grade 12, so leave that for now, and of course you can stop. So let's start with linear acceleration. What you're going to see is that the velocity vector and the acceleration vector will be shown. I'm not going to tell you which one is which. Let's see if you can guess which is which as the object moves. Check this out. So the mass is going back and forth. It speeds up to the left and stops. It speeds up to the right and then stops. Pause your video for a moment and see if you can guess which vector, the blue one or the green one, is velocity and which one is acceleration. Pause the video now and give it a try. Okay, and you're back. Let's get this going again and discuss. The object starts moving to the right. The green is representing the direction it's moving at all times. The green vector always points the direction that the object is moving, and therefore the green is velocity. The blue also points in the direction of the green, but then it reverses. It only reverses when the object slows down. The blue is actually the acceleration vector. It's telling you the direction of the change in velocity, even if the velocity is still pointing forward. So when you slow down, your acceleration vector is opposite the direction you're moving. I'll say that again, and you can watch with the object. When the object slows down, the acceleration vector in blue opposes velocity. That's what it means to slow down, in fact. To have an acceleration vector opposite velocity is slowing down. And if the acceleration vector is in the same direction as velocity, such as you see right now, then you're speeding up. And that, in a nutshell, is acceleration, at least in one dimension. Now let me show you something, just for fun, in 2 dimensions. We're going to do a little bit of circular motion here. Here you can see the object is moving in a circle, and as we mentioned earlier, the tangent direction is the direction of the velocity vector. So you see the green vector here pointing along a tangent to the path. That is your velocity at any moment. Of course, the velocity is changing. You see its direction changing, even if it's a steady circle with a steady magnitude, steady speed. The blue, which is the acceleration vector, is pointing perpendicular to the velocity. And now, if you want to know why that's the case, you're going to have to talk to my grade 12s. That's where we do circular motion in detail. But for you guys in grade 11 at this time, I think it's good enough to know that even in circular motion, 2-dimensional, the velocity vector is changing. And that would be true even if you weren't going in a circle. If you were just going kind of zigzagging all over the place, like you might if you were skating, just like figure skaters, for example. All right? There's other ones that you can try here. You can try linear acceleration part 2, which is a little bit trickier here. And then there's something called simple harmonic motion, where the object zigzags back and forth once again. And it would be very good for you to try to explain what's going on with both those vectors in terms of the motion of the object, speeding up, slowing down, going left, going right. If you want to keep things simple, click on this, show 1. This just shows the velocity vector, keeps things very simple. Show the other, this shows the acceleration vector. And of course, you can show both. All right, so anyway, back to our lesson here. I think we've pretty much covered everything. There was just one thing that I wanted to point out. Where was it? Actually, I think I did cover everything. Let's check that we covered everything. For some reason, I feel something is missing, but maybe it isn't. We've talked about what acceleration is in physics and how it's different than the term in English. We talked about some examples in 1 and 2 dimensions, and we did our simulation. At this time, make sure you can do some of these questions in the textbook here and here. And also check out these learning goals and success criteria that you can calculate the average acceleration of an object, and you can identify situations where an object is speeding up or slowing down by looking at the velocity vector at any moment. So yes, we have covered everything. And I know what I forgot now. It just popped into my mind. It's the fact of the day. And so what is going to be the fact of the day? The fact of the day is back to this slide that we saw about the circular motion. If you are moving in a circle at a steady rate, or in fact if you're moving along any curved path at a steady speed, which is what I meant to say, are you accelerating if that speed stays steady? Yeah, if your direction is changing, because that means your velocity is changing. All right, thanks for watching, folks. I will see you in class. Take care now.